In previous videos, we talked that across calcite R units, the light subdivides into rays, the ordinary and extraordinary rays. Is there a way to distinguish which is which? Yes, there is. But for that, we need to use the auxiliary plate, a gypsum plate in our case. Please note that not all light polarized microscopes have a slot for this auxiliary plate, but only those that are fully equipped petrographic microscopes like the one shown in the first video. First, you have to keep in mind that the gypsum plate is inserted oriented in such a way that it has the plane of lowest velocity aligned with the northeast-southwest orientation at 45 degrees from both polarizer and analyzer directions, or along the first and third quadrants, as you prefer. In this position, the gypsum plate produces a retardation of 530 nanometers, which corresponds to the first order purple in the Michel-Levy chart. So, when inserted, the gypsum plate gives a purplish color to the otherwise black color or extinction in cross polars. But it also gives a bluish and yellowish colors to opposite quadrants. Why? When an R unit crystal is rotated to be at maximum brightness, it has a retardation that normally corresponds to the first order white, let's say equal to 200 nanometers. In this position, it has its special planes, the optical plane and the normal equatorial plane, at 45 degrees from the polarizer or analyzer. But which is which? Or, in other words, where is the ordinary ray plane and where is the extraordinary plane orientation? To know that, we need to insert the gypsum plate. In these conditions, the faster calcite ray is slowed down by the slower gypsum ray, and retardation diminishes. The new value corresponds to the subtraction of both retardations. The retardation of the gypsum plate, 530 nanometers, minus the original retardation of the calcite crystal, 200 nanometers, which is equal to 330 nanometers. This retardation corresponds to a first-order yellow on the Michel-Levy chart. We can then memorize this orientation relative to the elongation or any other morphological particularity of the calcite crystallith. You can confirm this interpretation by rotating the crystal 90 degrees. This time, the retardation color should be the second-order blue. Why? Because this time, both the slower waves of the calcite and the gypsum are aligned, and so this configuration further slows down calcite's ordinary ray. In this condition, retardations of calcite and gypsum add to each other. The retardation of gypsum plate, 530 nanometers, plus the original retardation of the calcite crystal, 200 nanometers, equals to 730 nanometers, and this corresponds to the second order blue on the Michel-Levy chart. So, under cross polars, when we insert the gypsum plate and the retardation color changes from white to yellow, that means that the crystal has its optical axis and plane of vibration of the extraordinary ray in the northeast-southwest direction. In this example, the extraordinary ray, and so the optical or symmetric axes, are aligned with the maximum length of the crystallith. If retardation color changes from white to blue, this means that this time the crystal has its plane of vibration of the ordinary ray perpendicular to the optical axis in the northeast-southwest direction, aligned with their maximum length. The use of the gypsum plate is very useful in mineralogical determinations. For calcareous nanofossils, the mineral is almost always calcite. But even in these cases, the gypsum plate may be useful to distinguish different sets of crystalliths apart by evidencing distinct optical orientations between them. Let's test this, shall we? Okay, let's consider this round calcareous nanofossil composed of a series of single crystallites, the so-called elements, disposed radially. Some are illuminated, some others aren't. The ones that aren't illuminated have their special directions, the optical ray direction of the extraordinary ray and the perpendicular direction of the ordinary ray align with the polarizer and analyzer. And so, they don't rotate the light and become extinct under cross polars. Combined, they produce the two black extinction lines that cross in the central area, also black in this case because it's void of crystals. Note that the pattern maintains even when we rotate the coccoliths, which means that it is radially symmetrical. Note as well that while we rotate the calcareous nanofossil, it loses focus, and we need to focus it again. It's a bit annoying when we see it here on video, but don't worry, when observing them at the microscope, after a while, you'll not notice this. With time, you'll even get used to continuously focus and defocus a bit with the fine focus knob. This is useful to get a perspective of the third dimension of the calcareous nanofossil. For the other elements, their special axis makes an angle that varies from 0-something to 45 degrees relative to the polarizer and analyzer. So, they induce the light to rotate and they become illuminated in cross polars, as we described in previous videos. This means that the special orientation planes of the elements, since they are perpendicular to each other, must be aligned, one radially and the other tangentially, like shown here. We'll draw these planes in white until we are able to identify which is which. If it's the plane in which vibrates the extraordinary ray, we'll give it a red color. If it's the plane in which vibrates the ordinary ray, we'll give it the green color. Let's remember first that we are dealing with the mineral calcite, which has a negative optical signal. So, the extraordinary ray is the faster one and the ordinary ray is the slower one. Let's simplify the image now by removing those that are extinct. Let's simplify further and only keep the rays that vibrate parallel to the gypsum plate northeast, southwest. Now let's insert the gypsum plate. The first and third quadrants acquire a first-order yellow retardation color, while the second and fourth quadrants acquire a second-order blue retardation color. Can you identify the extraordinary and ordinary orientations? Right, yellow means that retardation decreased, retardations subtracted. So, the rays of calcite that are aligned with the slow gypsum ray are of opposite nature. So it's the faster extraordinary ray of calcite that is vibrating in the northeast-southwest direction. On the other hand, blue means that retardation increased, retardations added. So, in this case, the rays of calcite that are aligned with the slow gypsum ray are of the same nature. So, it's the slower ordinary ray of calcite that is vibrating in the northeast-southwest direction of this quadrant. Okay, let's return now to the cross polar's first image. First we draw the axes we deduced. Now we add the complementary rays. Now we add them in the north-south and east-west directions. And because we know that the extraordinary ray vibrates in the plane of the optical axis, we can draw the orientation of the optical axis for the several elements. And they all display radially. And that's why we call these elements as R of radial units. Let's do this exercise again for another calcareous nanofossil with a distinct shape. Let's consider this one with a basal disc and a claviform or baseball bat shaped spine. So, let's deduce the orientation of the optical axis relative to the baseball bat. In this position, with the baseball bat length at 45 degrees of both the polarizer and analyzer, By inserting gypsum plate, it turns to second order blue. This means that retardation adds. This happens because it's calcite's lower ordinary ray of the baseball bat that is aligned northeast-southwest. In this other position, it turns to first order yellow, so retardation subtracts. This happens because this time is calcite's extraordinary faster ray that is aligned northeast-southwest. Probably contrary to your first idea, this time the optical axis is not orientated along the length of the spine, but along its width. Let's do it a third time, shall we? This time I selected one of the elements of the Ascidian spicules I mentioned earlier. As I mentioned several times, these are made of aragonite, which is biaxial, but also negative, so the same rules for the gypsum plate applies. In this position, retardation subtracts, so it's the faster extraordinary ray that is aligned northeast-southwest. Note that the first order white retardation color of its thin edges becomes first order yellow. The thicker reddish purple area with a similar retardation color than the gypsum plate, by subtracting, cancelled each other out, and so it behaves similarly to an isotropic or nearly isotropic substance, and so display a darkish color. The thickest central area with the maximum retardation of a second order blue in Michel-Levy chart corresponding to 630 nanometers, by subtracting the gypsum retardation of 530 nanometers, it gives a very low retardation of 100 nanometers, corresponded to the grayish retardation color we see in the central area. In this position, retardation adds, so the slower ordinary ray is aligned northeast-southwest. The first order white of the thinner edges becomes blue, as we have seen before. The reddish purple looks like it kept the same colors, a bit brighter. In fact, it doubled its value and jumped from the first to the second order in Michel-Levy chart. The thicker blue area also became a little brighter, because it jumped from the second order blue to the third order blue-green. In conclusion, the optical axis of aragonite of this element of Ascidian spicule is aligned with its length.